In order for me to explain the VSEPR theory of molecules with 5 electron clouds, I carefully picked out 5 examples to explain the different geometries of different molecules that have 5 electron clouds. Okay, let's take a look at the first one. The first one says PF5. Okay, the first thing we have to do is to draw the Lewis structure. We know this already. If you've not checked this out, I would advise you check the previous videos on VSEPR theory of 2 electron clouds, 3 and 4 electron clouds. Okay, so P have 5 valence electrons, F have 7 valence electrons times 5, since we have 5 atoms here. So that will give me a total of 35 plus 5, that will give me a total of 40 valence electrons. Okay, the central atom here is phosphorus, since it has a lower electronegativity compared to phosphorus. So let's just add the 5 fluorine atoms. So let's just put it anywhere, doesn't matter for now. So we have F, we have F, we have F, we have one F here, and we have F. Okay, so we have 5 fluorine atoms now in my diagram. I've used up 10 electrons to form the bonds. So 10 from 40 will give me 30. So I assign the valence electrons now remaining to the terminal atoms now to complete their octet configuration. So let's do that. I assigned 6 electrons per fluorine atom times 5 fluorine atoms. That will give me 30. So remove 30 from this, I will have 0. So this is the Lewis structure for PF5. Next step is to count the number of electron clouds. So let's count that in orange. We have electron cloud over here, 1. We have 1 over here, 2. We have 1 over here, 3. We have 1 over here, 4. We have 1 over here, 5. So we see that the electron cloud geometry is something called trigonal by pyramidal. So let's see how this looks like. I may not really give a nice picture, but I think you get the idea. Where all these points are fluorines. So we have 5 fluorines, 1, 2, 3, 4, 5. And we have the central atom somewhere around there. That's the phosphorus. So this is called a trigonal bipyramidal geometry. So this is how it looks like. So the electron cloud geometry of PF5 is trigonal bipyramidal. The next or the last step is to ignore the lone pairs. Okay, are there any lone pairs on phosphorus? No. So hence the shape of this molecule is trigonal bipyramidal, since there is no lone pair on phosphorus. One thing you have to consider when it comes to 5 electron clouds, the arrangement are quite different. We adopt a kind of arrangement. Okay, let me use phosphorus and fluorine as the example. So we have something they call the axial arrangement, or let's say the axial groups. Okay, also they call the equatorial group. Now note that this kind of grouping is only peculiar to molecules that have 5 electron clouds. Let's say, for example, I have phosphorus as central atom, and I have my fluorine as terminal atoms. So where are the equatorial group? As what implies, equatorial means that they are equal distance from each other. So if you divide 3 say by 3, you have something like 120, right? So let's say we say this is 1 here, this is 1 here, and this is 1 here. Okay, so look at the bond angle between each one of them. Bond angle here is 120 degrees. The bond angle here is 120 degrees, and the bond angle here is 120 degrees. I think you get the idea why they call it equatorial now. So we have one terminal atom here, we have one terminal atom here, we have one terminal atom here. So these 3 fluorine atoms in orange, they are at what position? They are at equatorial position. Okay. Now for the axial group form angle 180 with each other. Let me use a different color for that. Let me use green. So look at this over here. Let me do that well. Look at this over here. Look at this over here. These flowing atoms in green are called the axial groups. Okay, are called the axial group. The angle between the axial group, the angle between them is 180 degrees. Okay, so this is how you arrange. You arrange in equatorial positions and also arrange in what in axial positions. So this is how PCL5 looks like the geometry of PCL5. This is how it looks like, something like this. I think you get the idea. And one thing you should notice is that the electron clouds formed by non-bonded electrons, that are in lone pairs, are usually placed where? They're usually placed in the equatorial positions. Okay, I'll show what I mean in the next example. We place electron clouds that are formed by lone pairs at equatorial positions. That means we place them, either we place them over here, or we place them here, or we place them here. Do you understand that? And we place the other ones at the axial positions. Again, one more time. The axial positions, the point angle between the axial group is 180 degrees, and the point angle between the equatorial groups is 120 degrees. But the point angle between an axial group and an equatorial group is 90. So the point angle here is 90 degrees. So between an equatorial group and axial group, the point angle is 90. The point angle here as well is also 90 because this is equatorial and this is axial. The point angle here is also what 90, but this is equatorial. Sorry, this is equatorial and this is what axial. Let's take the next example, SF4. Okay, for SF4, again, the first thing you have to do is to draw Lewis structure. S has 6 valence electron, F has a total of 7 valence electron times 4. This will give me 28. 28 plus 6 will give me a total of 34 valence electrons. Okay, so the terminal atom and the central atom, sulfur being or having a lesser negativity, will be the central atom. So we're going to have 4 flowing atoms. We have flowing here. Let's just draw that. This is just Lewis structure. We're still going to rearrange. So these are the flowing atoms. Okay, let's count how many electrons have I used up. I've used up 8 valence electron. So removing 8 from 34, we are going to have 26 valence electrons. So what do we do now? We complete the octet configuration of the terminal atoms by adding lone pairs of electrons. Let's do that real quick. So we have this to complete the octet configuration of each terminal atom. We add lone pairs. We add 6 plus 2 here already. That's 8. So that's 8 electrons in total. So I used 6 electrons per fluorine times 4. That will give me a total of 24 valence electrons. So how many valence electrons are left? We have just 2 left. So what do we do now? We assign the valence electron to the central atom. So let's assign that to the central atom. So that is it. So what do we do next? After drawing the Lewis structure, we count number of electron clouds. Okay, we have 1 electron cloud here. We have 1 electron cloud here. Electron cloud, don't forget, is the region of space where there's electron density, or where you can find electrons. So we have 1 here, we have 1 here, we have 1 here, and we have 1 here. We also have 1 here. Don't forget that lone pairs also form electron clouds. So we have 5 electron clouds. 1, 2, 3, 4, 5. So the electron cloud geometry, let me just write ECG for short, is still trigonal. It's trigonal by pyramidal. Trigonal by pyramidal. Okay, now to know the geometry of the molecule, the last step says you should ignore the lone pair. Before that, I told you something up here, up around here. I said that when it comes to 5 electron cloud, there is a different arrangement. So let's look at the arrangement. Okay, I mentioned that we have axial and equatorial positions. Okay, so let's say this is sulfur, our central atom. So where is my axial? Where is my equatorial? As I mentioned earlier, I said these points here are my equatorial. These are my equatorial positions, and these are my axial positions. Now, what do we place as equatorial positions? We place lone pairs. So this lone pair now, we place one of the equatorial positions in my diagram, I put one equatorial position here and I put two over here. So in my little practice, I realized that placing whenever you have one electron cloud, it's best to place them here. It's not really a rule or anything, but it's best to place them here. With that, it'll be easier for you to name the geometry of the molecule. Okay, so we place them here over here. The one that has the equatorial position with only one electron cloud. So we place that over here as this lone pair, place that over one of the equatorial positions. Now we have two other equatorial positions that will be here and here, right? Because the bond angle, don't forget, the bond angle between every equatorial position is 120 degrees. So here we have our fluid. That's one of the fluids. We have our fluid here. So our equatorial positions are filled up. We still have two more fluid atoms. So would have the okay, good. That will be at the what? At the axial position. Let me change the color for that. So we have one over here and we have one over here. Okay. So we have a fluid here and we have a fluid here. They are at what positions? At axial positions. And don't forget that the bond angle between axial positions, bond angle here is 180 degrees. While the bond angle between axial and equatorial is 90 degrees. Now naming the molecule now, the last rule says you should ignore the lone pair, right? So if you ignore the lone pair, as this is the lone pair over here, if you ignore it, what do you see? Something like a straight line. That's a straight line. And you see these two things like this, right? So let's try to like turn this. Let's turn it this way. Okay, something like this now, right? So imagine that we have a kid over here, down on this, and a kid over here, down on this. This looks like a seesaw. What kids play with. So this looks like a seesaw, right? So say the geometry of this molecule, sorry, is a seesaw geometry. Is a seesaw geometry. Right? I hope that is very clear. So from the way it looks like, we say this is a seesaw geometry. So SF4 has seesaw geometry. The next one we have CLF3. CLF3. Again, let us draw the level structure. So Cl, we have 7 valence electrons. Fluorine, we have 7 valence electrons as well. Times 3, so that 3 atoms, that will give me 21. 21 plus 7, that will give me a total of 28 valence electrons. So between fluorine and fluorine, which of them is the central atom? Chlorine is below fluorine, so chlorine should be the central atom. So we have chlorine and we have our fluorine. Let's just draw that anywhere since we are still going to redraw this molecule. So I've used up 2, 2, 2, that's 6. So minus 6, I will have a total of 22 valence electrons. So I will assign them now to the terminal atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 times 2, that will give me 18. Or let's recount. We have 6 here. 6 times 3 will give me 18. So subtract 18 from here. I will have a total of 4 valence electrons. Who do I assign this to now? I assign this to the central atom, which is chlorine. So I have a lone pair here and I have a lone pair. So this is the level structure for CLF3. The next step now is to count the number of electron clouds. So let's count. We have 1 here. We have 1 here. We have 1 here. That's 3. We have 1 over here. And we have 1 over here. So we have 1, 2, 3, 4, 5. So there are 5 electron clouds again. There are 5 electron clouds. So what do we do? What do we do? We know that the electron cloud geometry is trigonal bipyramidal. Before we can name the shape of this molecule, we need to redraw and place the right positions. So here we have chlorine as a central atom. Don't forget we have 2 kind of positions. We have the equatorials, that's something like this, equatorials, and we have the axial. Okay, so what do we place at equatorials? Don't forget to place what lone pairs at equatorials. And we have 3. Normally we have 3 equatorials. We have 1 over here. My diagram above, we have like this, isn't it? So 2 equatorials, we can place it here and here, or here and here, or here and here. The best is to place it on one side. makes more sense that way. And it's easier for us to get the geometry of the molecule. So let's place our lone pairs on equatorial positions. Let's do equatorial positions over here. So that means that we are left with one equatorial position that will be filled up by one of the fluorine. And what other position do we have? We have the axial. So we have something up here and one down here. So we have a fluorine up here and the fluorine down here. Okay, so we have correctly arranged the molecule. Okay, so the last step says you should ignore the lone pair, right? So if you ignore the lone pair, these are the lone pairs. So let's ignore it. What are you going to see? Something like this and something like this, isn't it? So if you turn this again, turn this like this, gives like a kind of, it forms a kind of T, right? So you say the shape of this molecule is T-shaped. So it has a T-shaped geometry. So ClF3 has a T-shaped geometry. Next example, we have I3 minus. So let's get down with this. We have I3 minus. I is iodine and is an halogen. So all halogens have 7 valence electrons. So we have times 3. That will give me 21. But since we have a negative charge, it means that this has gained 1 electron. So let's add 1 more electron to this. That will give me a total of 22 valence electrons. So since we have the same kind of molecule, so let's just write it linearly. So we have I, and I. So which of them will be the central atom? Obviously the one in the center. So let me change the color to make it obvious. So this is the central atom. Although they are all iodine, but this is the central. This is the middle of the 2 of them. Okay, so I've used up how many electrons now? I've used up 2 here, 2 here, that's 4. So subtract 4 from 22. This will give me 18 valence electrons. So let's assign the valence electrons now to terminal atoms. So we have this. So I've used up 6 here, and I used up 6 here. That will give me 12. So remove 12 from this. I'm going to have 6 valence electrons remaining. What do I do? It means 6 valence electrons. I will assign them to the central atom. So I have 1, I have 2. Let me put the last one down here. This is the Lewis structure of I3 minus. Okay, we have to put this in a kind of square braces since it's an ion. Okay, so let's count the number of electron clouds. So we have 1 here, we have 1 here, we have 1 here, we have 1 over here, and we have 1 over here. Let's count how many electron clouds do I have. This is 1, 2, 3, 4, 5 electron clouds. Remember that the electron cloud geometry is still trigonal bipyramidal. So for us to get the geometry of the molecule, what do we have to do? Let us rearrange axial and equatorial positions. So let's first draw the central atom, which is my LD. So we have 3 lone pairs. Again, where do we place lone pairs? We place lone pairs at equatorial positions. So we have one equatorial position over here. We have another over here. And we have the last one somewhere around here. So the bond angle, don't forget, the bond angle is 120 degrees between every equatorial position. Okay, let me take this off so it won't confuse us. So these are the 3 lone pairs now. So what other positions do we have, or groups? We have the axial group, right? So let me put that in red. So we have an iodine up here, and we have an iodine down here. Don't forget that the bond angle between axial groups is what? Is 180. So we have the angle here, the bond angle here should be around 180 degrees. So now let's name the shape of this molecule. Geometry of the molecule. What do? You ignore the lone pair. This is a lone pair, a lone pair, a lone pair. If you ignore them, what do you see? You see just a straight line. It's a kind of a straight line, right? So we say that I3 minus is linear. It has a linear geometry. Although the electron cloud geometry is trigonal bipyramidal, the geometry of the molecule itself is linear. And finally, we have XEF2. Again, the Lewis structure. We have 8 xenon. This is xenon. Xenon is a noble gas, and every noble gas has a stable of death. So it has 8. Fluorine has 7 times 2. That's 14. 14 plus 8 will give me a total of 22 valence electrons. Okay. So now the next thing is to get the central atom. Since xenon has lower negativity, does not have any love for electrons, so it will be the central atom. And our fluorine will be the terminal atom. So I've used up how many electrons here? I've used up 4. Remove 4 from our total of 22. We're going to have 18. 18 valence electrons. Do you know what to do now? We assign them to the terminal atoms. So let's assign them to the terminal atoms. So I've used up how many valence electrons you can count. So 6, 6 as 12. 12 from 18. That should give me 6 valence electrons. So I'll assign the remaining 6 valence electrons now to the central atom. So let's do that. I have 1 here, I have 1 here, and I have 1 over here. So this is the Lewis structure for XEF2. So let's count the electron clouds. We have 1 already. We have 1, we have 2, we have 3, we have 4, and we have 5. So the electron cloud geometry is still trigonal bipyramidal. But what's the geometry of the molecule itself? What do we do? Let us rearrange. I have Fe, Xe, other. So we have we have equatorial groups and axial groups. So for the equatorial group, we have one equatorial group over here, we have one over here, and we have one over here. These are 3 equatorial groups. I explained earlier that we place lone pairs at equatorial groups. That's why I place the 3 lone pairs here at equatorial groups. So the axial groups now, what do we place here now? We place other atoms. So we have fluorine. So I've placed fluorine up here and down here. So if you ignore the lone pair, ignore this, and ignore this. What do you see? You see a kind of a straight line. Okay. So you say the geometry of the molecule is linear.